Scientifically, electricity is the flow of electrical power or charge. It turns on the TV, cooks dinner, washes and dries your clothes, and lights up the house at night. In a broader sense, electricity is a controllable and convenient form of energy used in a range of applications of heat, light, and power. It's so universal and such an important part of everyday life that we rarely stop and think about electricity and what we would do without it. So let's dig a little deeper and see what electricity is all about. We start with the atom. Everything in the universe is made up of atoms. Every star, every tree, every animal. The human body is made up of atoms. Air and water are too. Atoms are the building blocks of the universe. Atoms are so small that millions of them would fit on the head of a pin. Atoms are made up of even smaller particles. The nucleus in the center, made of protons and neutrons, and then buzzing around the nucleus are the electrons. Protons and neutrons are very small, and the electron is even smaller. Think of a tennis ball as the center, or the nucleus, and ping pong balls are the electrons spinning around the tennis ball. The electrons are negatively charged, and the protons are positively charged. The neutrons, as the name implies, are neutral. The electrons are attracted to the protons and are held in an orbit around the nucleus. As they spin, they are also trying to stay away from other electrons. Think of two magnets. When the negative ends are moved closer together, they push away from one another. In the same sense, the protons and electrons act like the positive and negative ends of the magnets that pull together when moved toward each other. We say an atom is in balance when it has an equal number of protons and electrons. The neutrons carry no charge, and the number of neutrons can be different without affecting the balance of the atom. Now here's where it gets interesting. The number of protons in the atom tells us what element it is. An element is a substance in which all the atoms are identical. But we want to discuss electricity, so for our purposes, we need to remember that a balanced atom has the same number of protons and electrons, and that different elements have different numbers of protons. For example, hydrogen has 1 proton and 1 electron and no neutrons. Carbon has 6 protons, 6 electrons, and 6 neutrons. This is important when we talk about electricity. Electrons usually remain a constant distance from the nucleus and move in orbits called shells. There can be any number of shells for each atom, determined by the number of electrons. The shell closest to the nucleus can hold 2 electrons. The next shell can hold up to 8. The outer shells hold even more. But as you move away from the protons in the nucleus, the pull on the electrons decreases, making it easier for these electrons to be pushed out of their orbits. Applying a force can even make them move from one atom to another. These moving electrons are electricity. Because electricity is such an important part of our daily lives, we don't think of it like this, but electricity is actually a secondary energy source. We get it from the conversion of primary sources like coal, natural gas, oil, or nuclear power. We've all heard and used the term generate electricity. There are generation plants in our communities making electricity for use in our homes and businesses. An electric utility power station uses a turbine, engine, water wheel, or some type of machine to drive an electric generator or a device that converts mechanical or chemical energy to electricity. Most of the electricity in the United States is produced in steam turbines. A turbine converts the kinetic energy of a moving fluid, either a liquid or a gas, to mechanical energy. Steam turbines have a series of blades mounted on a shaft. The steam is forced against the blades, which turn the shaft that is connected to the generator that makes electricity. So how do we get the steam? In the U.S., plants burn fossil fuels to heat water that makes the steam that pushes the blades, that turns the shaft, that drives the generator that makes electricity. Most power plants are about 35% efficient. That means for every 100 units of energy that go into a plant, only 35 units are converted to usable electric energy. That's a lot of burning coal for not so much electricity. There are several ways to make electricity. Take a look at this chart. It shows energy production using methods like fossil fuels, nuclear power, and renewable energy.
And action.
Electricity travels in closed loops or circuits. It must have a complete path before the electrons can move. The basic layout of the circuit includes the source of electricity, a load, and two wires to carry electricity between the two. Electrons move from the source through the load back to the source. When you turn on a light switch, you close the circuit. The electricity flows from the electric wire through the light and back into the wire, and it keeps flowing until the circuit's interrupted. Turn off the switch and the circuit is open. The flow stops. Take this scene a step further. Many circuits can be linked together. Power coming into the building can be shuttled into many circuits, bringing electricity to individual rooms and appliances that can be controlled with a switch. Here's where we really see the controllability aspect and ultimately the convenience we enjoy today. Now let's get back to the science of it all. Moving electrons have energy. As electrons move from one point to another, they do work. In the light bulb example, the energy of the electrons creates heat, and the heat creates light. Apply this to every electric appliance you use today. Each one harnesses the energy of electrons in some way to create energy that is useful in our daily lives. Let's get some details out of the way before we continue. First, some essential definitions of terms commonly used when discussing electricity. The number of electrons in motion in a circuit is the current, and it's measured in amps. The force that is moving the electrons along the circuit is the voltage, and it's measured in volts. Here in the U.S., the power outlets in your house or business deliver 110 volts. These terms define how we measure the amount of energy consumed. To get watts, multiply the amps by the volts. You can do this for any electrical appliance. Then we graduate to kilowatts and megawatts. These, as the names imply, are large quantities. A kilowatt is 1,000 watts. A megawatt is 1,000 kilowatts. So much energy flows out of power plants to so many houses and businesses in so many cities and towns for so many uses, it would be impossible to deal strictly in watts. All those zeros get very confusing. So simply put, 1 megawatt equals 1,000 kilowatts equals 100,000 watts. See what I mean about the zeros? In practical terms, 12,000 watts is written 1.2 kilowatts, and it wouldn't be talked about in terms of megawatts. And 12,000 kilowatts would be written 1.2 megawatts, and it wouldn't be talked about in terms of watts. But if you really want to know, that's 12 million watts. There's one more unit of measure, the kilowatt hour. A kilowatt hour, written kWh, is equal to the energy of 1,000 watts working for 1 hour. The amount of electricity a power plant generates or a customer uses over a period of time is measured in kilowatt hours. This is determined by multiplying the number of kilowatts required by the appliance or all the electronics in use by the number of hours of use. Back in the 1880s, William Stanley invented the induction coil that eventually became the transformer we know today. The transformer makes it possible for electricity to be efficiently transmitted over long distances, ultimately supplying it to homes and businesses at voltages that are safe to use every day. Here's an illustration. The electricity produced by a generator travels along cables to a transformer, which changes electricity from low voltage to high voltage. Electricity can be moved long distances more efficiently using high voltage. Transmission lines carry this high voltage electricity to a substation. Substations have transformers that change the high voltage electricity into lower voltage electricity. From the substation, distribution lines carry the electricity to homes, offices, and factory, which require low voltage electricity. Got it? Great. Now think really big. Just as individual circuits can be linked together, making a complex network of useful electrical applications, generators, transformers, power lines, and substations can be linked together, creating a complex network that's called the grid. On the grid means you're getting power from plants that are generating electricity from primary sources and sending it out on lines using transformers and substations and more lines to get it to you for everyday use. Off the grid means that you're generating your own electricity for your own use without being connected to the grid. Grid-tied systems are generally where renewable energy sources like solar or wind are used to make electricity at your home or business, and that electricity is used on site. But your home or business is still connected to the grid, so you can get electricity from the power plant when needed, or even send the power you make on site back to the power plant. AC power is a term that is widely used when discussing electricity used in homes or offices. By definition, AC is alternating current, and it's the type of electricity used to power common household appliances. DC is direct current, and it's made by fuel cells, solar cells, and batteries. Here's the science. Using a battery, for example, there are always two terminals, one positive and one negative, and the current always flows in the same direction between those terminals. AC power is what comes out of a power plant. Alternating current is just what it says. The current alternates directions. Here in the United States, this happens 60 times per second. Here's another way to put it. The power that is available in a wall socket is 110 volts, or 60 cycle AC power. If you're using a solar cell to generate direct current, that electricity must be converted into alternating current for use in your home or business. No problem. There's a tool for that. It's just an additional step that is essential for off-the-grid or grid-tied renewable energy systems. Perhaps the best known of all inventors of electricity is Benjamin Franklin. His famous experience with a kite and a key in a lightning storm set it all in motion, and many of the principles of electricity used to guide subsequent experiments and inventions were founded on that one night back in 1752. History might argue that Franklin never performed that actual experiment, but he published a paper in 1750 on the concept, and many experiments were done based on his writings. Thomas Edison changed everything with the light bulb. 1879 saw the first commercially practical incandescent electric lamp. This bulb maintained its incandescence for over 40 hours. Prior to this, direct current electricity had been used in arc lights for outdoor lighting. A very dangerous practice, but one that extended the workday and provided an alternative to candles and torches. In the late 1800s, Nikola Tesla pioneered the generation, transmission, and use of alternating current electricity. As this form can be transmitted over much greater distances than direct current, Tesla's inventions used electricity to bring indoor lighting to homes and to power industrial machines, spurring the Industrial Revolution.